Hello, everyone. Welcome to the Active Inference Institute. This is Cohort 8, and we are looking at Chapter 2 of the Active Inference textbook. We're still in the first half of the book, so we're looking at a lot more theory, a lot less practice, but it's with Chapter 2 that we suddenly find ourselves getting plunged into a variety of terms, many of which will be familiar to folks who are interested or already familiar with probability theory, statistics, uh, Bayesian theory, information theory, working potentially with matrices for some of our examples, um, and yeah, statistics in general. So a lot of this sometimes comes off as intimidating to those who don't necessarily have a mathematical background. I do promise it's worth bearing through it, if only to become more familiar with the terms and to try and get what you can out of some of the more sort of somewhat more commonsensical, maybe that's not quite the right word, but examples of, if you observe something jumping, is it an apple or is it a frog? Right? It's like being able to rephrase things in rather simpler terms helps to clarify. Meanwhile, for those who are familiar with a lot of these terms, we're also introduced to kind of the framing for looking at things like expectations, surprise, how do we tie together biological inference with Bayesian theory? What is the difference between surprisal versus Bayesian surprise? And some of these kind of key figures in the textbook really help to paint more of a picture. Uh, I say tongue in cheek as we look at a picture. Um, in trying to understand something like how an action perception loop works. Now, we've already been through the course of this chapter introduced the idea of an agent on or a generative model. There are arguments as to whether the agent is its generative model or perhaps it's just equipped with a generative model. In either case, this generative model is essentially representative of whatever kind of problem or task the agent is trying to solve or faces. Um, and then we also have the generative process, which can comes off as a synonym here for the environment. So there's the notion of a Markov blanket, which is also incredibly central to active inference. And Daniel and I were just chatting about it just prior to this session. And so we notice there's nothing here directly connecting the agent and the environment other than this Y here, this observation. That's what is emitted by the quote unquote true hidden state of the environment, denoted by X asterisk here. And then that's used to infer the hidden state in the mind, so to speak, the generative model of the agent. We notice we have these dashed lines denoting sort of the Markov blankets. And I think the authors themselves note this, the U for action, just as the agent takes in the Y, the observations, the agent emits an action. Um, it it shouldn't be too mixed up. This U later figures back in a later figure, and it might be a little difficult to understand that it's actually an active state. It might be better represented here between the just as Y is between them, U should also be between the model and the process. Those are the sensory Y and active U states that kind of define like these boundaries and also nonetheless are sort of the vicarious pipelines or passageways almost between the Markov blankets of the agent versus the environment. Other ideas we're introduced to are that are very important is that the way that the agent models the true state of the environment, it's always more or less attempting to approximate something from the environment. That said, there's no necessity that this X is equivalent to the true state. In fact, there's not even a necessity that this X is structured equivalently to the true state. If If I'm hungry and I'm tired, uh, there's no necessity that I think that I'm hungry and I'm tired. I might be thinking in very different ways about those things. Um, so th that's just an attempt to give you a quick view of sort of what active inference is really looking at. Ultimately, we have a partially observable environment, meaning we can't actually see the real environment. We're always kind of vicariously like trying to interpret it and understand it through our sensory observations, perception, and through action. We are active inferers. We don't simply take in passive observations. Or rather, we don't passively take in observations. We emit actions as well. That, in fact, goes on to condition the environment around us, which then elicits new observations. So we can kind of see how the model and the process each have their own kind of respective logics, which can work incredibly similarly, but they also don't have to, or at least they don't have to be structured the same. If I knock on wood because it makes me feel better, is it actually doing anything other than kind of making me feel better? Sometimes I do it anyway because I know it makes me feel better because I have that mental association. It's that sort of logic that I'm trying to get at. And so that it's just a reminder action as inference. We act. It's part of the inferential process, right? And then some other key ideas are looking at like minimizing variational free energy. This essentially what we're trying to do, or the claim of active inference, as well as potentially the Bayesian brain hypothesis and other related areas, but this is of course looking directly at the FEP, the free energy principle. Um, we're looking at trying to minimize our uncertainty. Of course, uncertainty, prediction error, variational free energy, expected free energy, surprisal, Bayesian surprise. These are all various terms that we find through the book. They all do have their own nuances to them. They come into play at different times. Um, but in some sense, they're very relatable, conceptually at least. But for variational free energy, this is kind of the trick, and it's not just a trick. It plays out mathematically, and we see it with Jane's inequality. But variational free energy, the whole reason why we're doing this, compute why if the goal is to just minimize our surprise, so that we can better understand everything, why are we including this variational free energy term? Why do we have a variational free energy term? Why do we have a free energy principle at all? The idea is that surprisal is unfortunately very difficult to compute. Um, for those who have worked with, let's say, like deep learning and neural networks, right? If you have a fully connected network, there's an immense amount of information being passed. Depending on how you set up your parameters and what kind of state spaces you're working with, you quickly run into issues of intractability, where it's something just quite literally like does not compute. Um, Similarly here, uh, with variational free energy, the idea is that we get an approximation of surprisal. It plays out really well because through Jane's inequality, which we'll get to later, probably in a couple of weeks with chapter 4, I think is where it is. Uh, what it allows us to do is say, okay, well, we can't directly compute surprisal, but based upon particular assumptions, as well as mathematical like proofs and how it plays out, surprise can actually be upper bounded by variational free energy. There's no necessity that variational free energy equates to surprise, but it is a very fair approximation. And we know that surprise might not be equivalent, but we know that it won't be any higher than variational free energy. With variational free energy, by doing things like mean field approximation, being able to sort of marginalize out variables from joint distributions and so on, we essentially are kind of carving things up in a way that is easier to work with. Um, it's found through different neurobiological studies, in fact, that we do engage in approximate methods. It would be very taxing on us. If not intractable, it'd be incredibly taxing on us to perfectly compute everything at any given moment, including trying to minimize our uncertainty. And that's not even getting into the other sensory aspects, which is like, just because I can see everything in my field of vision, it doesn't mean that I'm actually processing very intently every single bit of what I'm taking in. We're very biased towards things that tend to be interesting to us, aligned with our goals in terms of pragmatic value, or things that interest us that we might learn from in terms of epistemic value. So with free energy, we see that there's this process of kind of engaging in free energy minimization relative to our engagement with the uh, environment, both through perception, changing your mind to minimize the difference. Oh, I thought it was 5 o'clock, but I look at the time, it's actually 6:16. I'm going to change my mind. It is 6:16. Or action to change the world. I am hungry. I'm going to eat food. Now I'm no longer hungry. In this case, has to do with the idea of interoception. I'm reading my own signals from my body. In that instance, it's as if my own body is the environment for me, right? Uh, there's a nice neuroscientist, Yori Busaki, who said that the brain doesn't know. I think Lisa Feldman Barrett said this too. It's a bunch of neurons, right? So, and many other things too. But it's conceptually very interesting. So, um, I've been going for some time. Expected free energy. We'll just touch on that real quick. Um, I used earlier this phrase, pragmatic value, right? Food is in my environment. I'm hungry. I expect to not be hungry. So I will take an action that minimizes expected free energy in order to sate my hunger by eating the food. That is my action. Information gain. I already mentioned that earlier. I thought it was 5 o'clock. I checked the time. Turns out I have new information. I didn't really accomplish too much, but I did learn something. Those are some kind of more everyday ways of attempting to describe how these dynamics play out. These kinds of equations are very important to be able to get some intuitive grasp of, especially if you're still wading your way through the textbook. Um, it's great. Part of the strength of active inference that I've always appreciated is being able to apply these sort of more qualitative terms to different aspects of active inference, such that you don't necessarily have to know all of the underlying maths in order to talk about active inference or do research in active inference or write about it. Um, you don't necessarily need to know it in any kind of deep, sophisticated way, as long as you're able to link the terms up appropriately. Never a bad idea to work with a computational modeler or a statistician or otherwise to really clarify your thoughts. But nonetheless, um, very possible. There have been many interesting papers written in active inference on phenomenology, cognitive science, social theory, uh, imagining ways that we could apply active inference to a variety of fields, mental health. Um, so um, there's plenty in this chapter. I believe it's the longest chapter in the book. Um, there's a lot we could touch on. So um, is anyone interested in talking about any piece of this or anything that stuck out or any curiosities, questions that came up over the course of reading it? Yeah, Stephen, please go for it.
I apologize if there's background noise. I just wanted to say that in going over the chapter and looking at some YouTube videos to try to understand it better, I found Artem Kirsanov's YouTube on the cross entropy uh, term, or the reason why that is used, separating out that the Q value, the I don't know all the terms, but where you don't have to do the complete computations, you just know what the divergence is.
Hmm.
It was what really clicked for me was the variational, um, what's it called? Variational free energy, variational probability. Um,
Okay.
uh, Using the analogy of image generation from deep learning, um, drawing from the probability configuration, the data structure of images that they were trained on. And in the in the brain, of course, the data structure that we're trained on is the world. And and the brain learns the data structure just from trial and error, from experience. So the brain figures out the variational free energy. I mean, it um, is it's deriving, or it yeah, learns the variational free energy from, what are the probability data structures of the world, which is why the more experience a person has, the better predictions one makes. The more interaction with the actual world instead of simulations of the world or imaginations of the world, the better the predictions become. I mean, it just this the explanation helped me understand why variational free energy is the right framing. Um, Comparing it to the brain, how it grows and develops, and what we're left with. Um, I, I had a question. I wonder if it's okay to ask. Um, you can tell me if this will be covered later, but I always want to try to see how this is being applied in the sense of the way the nervous system is set up, where there is constant sensory input and motor output, but that motor output is both sent to the effectors, but also sent to the internal model. And
Mm.
the internal model, or motor, uh, a copy of the motor command, is sent to a what we're going to call the internal model, but the networks that will respond to whatever the motor effectors are doing. And it's comparing, are the predicted sensory responses the same as the actual sensory responses?
Mm. Right.
And when there's a
Yeah.
difference, then the model is updated, or the neuron synaptic weights are changed. And I'm wondering, how can I see that in this active inference model, like in the figure that you just showed, uh,
Hmm.
where there's the internal model and then there's the world, and we're updating the model. It didn't look, in my mind, there are parallel paths. There's the motor command and the internal copy. It's called the Inference copy motor command.
Hmm.
And the internal motor command is creating a it's activating a internal model of the sensory input that would be the result of that motor command, which is then compared with the actual sensory input of that motor command. And that's the
Yeah.
way we're continually improving the actual motor commands.
So, yeah, so I will say you will definitely get more out of this textbook in terms of what it is you're describing and what you're interested in. I just want to quickly find, because there are many Not trying to give anyone, whiplash here, but I'm just kind of jumping around a little bit. So with chapter, I think it's at the end of chapter 8, and I'll just hang on this figure for a bit. Um, yeah. So a few different things. And this is more like, there will be some loose ends that kind of open up here, but a few terms you might want to look for in the textbook. That's the fortunate thing about this being freely, downloadable online and pulling up a PDF and just hitting Control F to just kind of zoom around through the textbook. A few phrases are proprioception, sensory attenuation. Um, this might relate as well in terms of like trying to directly model some of the dynamics you're describing, which are this would be a what is at once a hierarchical and mixed or hybrid model. And it doesn't necessarily have to be hybrid, but all those things. First, proprioception um, is related to kind of like so with the inactive inference, we have what are called observation modalities. It's a formal term, certainly not unique to active inference, but it's, my eyes allow me to see, and so I have a visual observation modality. And so it's like I'm taking in visual information. So you can think of that as a data stream, and I have the receptor or the sensory receptor for accepting visual stimuli or observations, right? Um, and then there's exteroception or exteroceptive observation modalities, which would kind of be describing things that are coming from without. These are very cognitive, kind of neuroscience related terms. So, they're kind of human centered or at least organism centered. But interoception would be signals coming from within. Exteroceptive signals would be those coming from without. And then proprioceptive would actually have a lot more to do with kind of movement. It could be, in the sense of like a reflex arc, for example. Um, so from there, sensory attenuation, which is always something interesting to wrap one's head around. In active inference, it comes off as a little counterintuitive, but actually, once I understood it, it was one of the most fascinating concepts they have, and it makes sense from within the framework, which is much of active inference, given the Bayesian lens, we're always bringing some kind of prior or what you expect to the situation. What you that includes priors on hidden states, like what you infer to be going on. But then there's also priors about observations, right? And so whenever you're describing this kind of aspect of having a model up for the sensory stimuli itself or the data stream, where it has to figure out what the observations themselves mean. You could view that as and then once it kind of figures out what they mean, it sends that further to another part of, say, a model to engage in further or deeper inference. Here, this hybrid model is kind of saying at this very fast time scale, I'm taking in these Y observations rather quickly, right? At each step of this slower model up here, a single, this is t minus one or tau minus one. So at one time step at the higher level, we actually have three time steps at the lower. So the idea is that at different levels, you can have different time scales of the inference process. But all this is to say, and I'll try to, because I prefer to clarify more than I make ambiguous, an answer to your question. But it would be something like you could model what does the incoming data mean, and then from there, based on what you think it means, how does that fit into another inference process for making higher order decisions or making higher order inferences? And given the whole partial observable paradigm, it is, I mean, yeah, there's no necessity that the data you receive is one to one with the real environment. I mean, this account, given the, the more human centric or organism centric, robotics centric aspects of active inference. It's like what happens whenever you have a bad sensory receptor, right? Like you still have to kind of figure out what an observation is or means. And so you can imagine, like in a more realistic sense, I mean, this could be an incredibly long, complex, like deep um, model here, where so many different inference processes are happening in different time scales, layering things up. Then the only thing is, why do any kind of modeling if in reality everything is that complicated, or at least we think it is? Well, with active inference as well as any other form of machine learning or deep learning, we're ultimately just trying to come up with a good model that generally approximates the phenomena of interest, or at least can predict on it. Um, and it needs to be not too complex, otherwise it'll overfit, and also be computationally inefficient. Kind of like me describing like earlier, like if I took in every single bit of information and computed every single bit of information, every bit of surprisal that there could be, I mean, I'm either going to hit intractability or massive exhaustion in a certain way. Um, and yet accuracy. So I want it to be good. And I guess referring to where you started with variational free energy, that's right. I mean, it would be to approximate. So to create a model itself isn't just to try and be hyper accurate. That's not just because of intractability or difficulty. It's also because it might not be a good idea to do that as soon as there's some kind of paradigm shift in the environment, right? So, like, if I'm in my home versus in a car, I will act very differently, right? Um, if I am overfit or I do overfit my generative model to being indoors, then as soon as you put me in a driver's seat, I will have no idea what to do. Everything will be very surprising. Any kind of strategy I would have will be biased towards something I would do indoors. It would be problematic. So having approximation and generalizability goes beyond just, you know, any kind of cheap trick. Not that anyone has said that, but it's not so simple. It actually helps for adaptation, right? So,
Yeah,
um,
if I could, that was
yeah.
wonderful. The the nervous system, of course, is composed of 10 to the 10th individual predictor, models, neurons, and it's organized to selectively suppress everything but what is needed at the moment. And I see what you're showing is kind of giving an example of that. If on so many different levels, from the reflex level to the cognitive, no, I want to be doing this now, and centering attention on one particular model.
Yeah. No, that's great. I'm glad this was helpful. And so this model here is just jumping to chapter 8, right? So this is way beyond where anyone, who has just started the textbook and they're only at chapter 2 now, like that, they wouldn't even have to consider any of these pieces of architecture yet, other than a couple things. Like we saw the Y earlier, your observations, and then X, the hidden states. But all of this about G, about F, functions, about, etas and so on, A matrices, that hasn't quite figured yet. We do have G, expected free energy. So it's kind of like this is, it is a textbook. So you can certainly like kind of build your way up to this. And frankly, I think this would be one of the most complex models that's shown throughout the textbook. Um, yeah, by the time we get to chapter 9, it actually reverts to, well, not reverts, but this is more about model-based data analysis. So this is more about kind of taking what we've learned, adding on a few other forms of analysis for kind of like understanding our models, or building or iterating over building models, and even fitting models, and then using them for, by fitting them, we can get into kind of empirical data analysis as well as like if you're working with groups of individuals that you're analyzing, right? Then you can look at summary statistics or other kinds of analyses per group. Um, but it's really just getting that initial intuitive grasp. Figure 9.1 has always been kind of fun. It's this is a POMDP model, which is just a discrete state space model, which you could use. It's not dramatically. There's certain kinds of conceptual overlaps this could happen with like a hot field network or something along those lines, where it's like you could have states just being a neuron's charge being positive or negative, or something is excitatory or inhibitory or otherwise kind of like discrete valued. But anyway, the bigger point of this figure 9.1 as we zoom out is that we're just being aware, like we, the experimenters, have our own idea of what the model is and what it should be. So it's rather meta, but I've kind of appreciated this sort of self-awareness that active inference practices, because at the end of the day, we are making a lot of decisions. Anyone working with neuroimaging data or otherwise is making a lot of decisions whenever they start modeling. And there are things that, will be these kind of blaring, never leave the back of your mind, like sort of issues with modeling that are like, oh, I need to include that, but I have no idea how, and I can't even, so we have to make certain kinds of like hard decisions sometimes when it comes to modeling. And to bring it back, um, that would be sort of the case for organisms too, right? Like all this computational modeling we're doing based on textbooks like this and reinforcement learning and so on. And apologies if I'm getting too abstract or philosophical, but it's like similarly, you could think of the brain as like, well, if I start a new job, place of employment, and I'm trying to figure out like, how does this work? What are my social dynamics with my coworkers? What is kind of our degree of professionalism and how do we sort out doing meetings and who is the best person to talk to about this topic and all kinds of things. I'm going to have to start kind of at least implicitly modeling how this goes because I'm going to presumably be engaging with my job like, X number of hours per week or, you know, scheduled meetings or otherwise. So in any scenario we come to, whether it be trying to model, myself properly engaging in my position of employment, or it be us trying to model how a mouse in a team maze behavioral task, functions and how it is that they infer where the reward is on the left side or the right side of the team maze, and what are the steps that they take to get there, and how do they decide that or determine that based on their sensory observations. I mean, it's just a lot of modeling to do, and it's almost always approximate. Life moves quickly. Um, I mentioned sensory attenuation too earlier. That's kind of a fun one, but I don't want to introduce too much too quickly. Let's see if this is a good place to pick up on that. The implication is that we need to be able to attend away from proprioceptive data by turning down their gain. This gain is given by the precision or inverse variance with which these data are predicted. To attenuate this, we need descending motor tracks to predict not just the data, but the precision of or confidence placed in those data, decreasing this precision to initiate movement. While this for some will come off as a very complex passage, and it really is, but this is chapter 5, so there's a good deal that you'll have learned by the time you reach this area. Sensory attenuation is interesting in part because like as sort of a learning heuristic for active inference, I think, because what it what it revolves around is this sort of Bayesian paradigm that is we bring our own beliefs to the situation, and a lot of things have to do with expectations, right? So there's a kind of strange philosophical conundrum that can come up when considering that. Well, if you expect that right now you are sitting in place, you might have a goal to, I might have a goal to stand up, but currently I expect myself to be sitting. That's what I'm observing right now. I notice I'm still sitting down. So how, if it's the case that we engage in like Bayesian inference, then how is it that I ever get up from the chair at all if my priors or expectations are always reinforcing, um, what I'm doing or what I expect, and that's influencing my action. And so sensory attenuation is the sense that in everyday terms, very everyday terms, because I noticed the time and I'm kind of droning a little bit about this, but the idea would be that it's almost as if your sensory receptors have to not pause, but heavily turn down their own game. Like in order to actually finally get up out of the chair, I have to, it's almost as if I'm forgetting that I'm in the chair. I need to move in order to make something happen. And so it's a rather interesting framing for looking at how we actually accomplish goals while reconciling this idea of, you know, the fact that we're always inferring. Um, Give me just 1 second because I realize the chat's been very active. Um, cool. Let's see, there was a question about this is backtracking, but let's because it'd be good to get ourselves recentered in chapter 2. Been taking us on a journey. Um, so expected free energy, we'll go to that equation. I will look a little bit more at some of these terms. So like here, there's a question about pragmatic value. So what is this? The expectation of the natural log of the conditional probability distribution y with a tilde, meaning it's a sequence or it can be a sequence, one plus elements in the sequence, conditioned on C. So I don't know if it was nice of the authors or not to so quickly introduce us to G whenever we're still missing some things like what is C. But that's okay. So C here, I mentioned earlier the POMDP model that we were looking at, which is for discrete state spaces. I was zooming in on those figures in chapter 8 and chapter 9. The C is a term denoting your priors over observations. So this is kind of like saying, if we just reduce to this, it's kind of like what is the probability of this sequence of observations conditioned on the observations I expect. And so pragmatic value is the idea, it's very much related or almost the way it's used is almost identical to the idea of reward seeking. It has so it's not about seeking out information for its own sake to change your mind. It's about directly going to an reward. If I expect to not be hungry, then if I'm observing that I'm in fact not hungry or I'm then this probability is going to be very high, right? Like my model is accurate in terms of achieving pragmatic value on the hunger end of things.
Okay.
Um, yeah.
From the text, it said the C is the preferences. So basically,
Yep.
this probability is the probability that you see the observations that you would want to see, right? Because it means you have the string of observations in the world that is your preferences, which means you get which means you get the observations that you want to see, and it's the probability of that. Couple of questions though. Why the logarithm? And also, it has to do with the probability that you see what you want to see, but it doesn't say anything about how much you want to see what you want to see. Typically, pragmatic value isn't about just how likely you are to get what you want, but how much you actually want what you want.
Yeah,
Hmm.
just a few quick
Yeah,
answers
go for
there.
it. Go for it.
The shape of C is a distribution over the observations. It does exactly tell you how much you prefer different observations. Like you could have 131 or 121. That's a sharper preference in the second case. Why is it a log? Um, there are several convenient properties of logs for probability, which is why likelihood distributions are often framed in terms of log likelihoods. For example, yeah, exactly, like those are the different sharpnesses. But log allow properties like log of AB is log of A plus log of B. So if you have two independent probabilities, you can separate them. So those are basic log properties. And also for computation, when you're dealing with low probabilities, it's easier to store a negative log as a large number, like 1 billion, rather than a tiny number. And it has properties that are important for statistics mapping between the 0 to 1 interval. So there's a ton of reasons why logs are used in general in statistics. All of those are in play. And then the preferences are a distribution over observations, and they can express the strength and the directions of preferences.
Yeah. Thanks, Dan. Oh, let's have another quick look at that. Exactly. So it's kind of like, just as Daniel mentioned, like if C is sort of a distribution over all of your preferred or expected observations, and then you get a sequence of observations, and you could view this, in the POMDP in the discrete state space setting, you could view this as like, oh, there are three different possible observations. I prefer the first one with full probability 1.0. The other two is 0, which means I completely do not want observation index 2 or 3. I just want the first possibility out of the three. Um, so like I'm I'm hungry, I'm completely famished, or I am fully sated. I prefer being fully sated, right? So the sequence of observations could be, an observation of being fully sated, not the others. And then once again, being fully sated, not the others. But then for maybe a third time step, now I'm hungry, right? So there would be, you know, of course, I'm just kind of making this up as we go, but so that would mean this probability would not be exactly one. If I were sated for all three of those time steps, then it would be one, right? So that'd be exactly what I expect. And then it's called expected free energy. And that's some folks are like, well, why do we have a variational and then we have an expected? The, and why is it called expected? And so with expected free energy, this is free energy of the future, so to speak. And it does kind of have its own um, set of equations to it, but we'll notice that it's being scored for each action or policy that can be taken. So a policy would be a whole sequence of actions into the future. And so whereas F is pretty, let's say, reactive in a sense, in that it takes in an observation, computing free energy to compute your posterior over states, meaning I took in this observation. What is the free energy that helps me reach the sort of optimal approximate posterior over states? If my stomach growls, best inference would be I'm hungry, probably. Expected free energy will be, oh, there's a series of things I could do in the sense of actions and sequences of actions I could take. So, given I could take an action associated with a sequence, like I could get up and go to the store to get food. Um, by the end of that sequence, at least, hopefully it at some point involves me eating the food and no longer being hungry, right? So to think about it computationally, it's simply that G is just scoring each of the kind of actions or policy sequences of actions that you could take. We want to minimize G as our optimization function. These two terms is kind of all you need. Um, you could look at these others too, but for now we'll just focus on this. Um, this is kind of like saying by doing a set of actions, what will be its pragmatic value? How closely does it match my expected observations, my preferences, what I want? Which from a more general perspective, C could well be what defines your constraints for maintaining homeostasis. So C could also be, oh, my blood oxygen level is, at a proper balance, or uh, hunger. I keep going to that one. That's a pretty good example of achieving homeostasis to make sure your caloric balance is in place. And then information gain is kind of like it's interesting because as opposed to variational free energy, where KL divergence is, it's kind of we want to minimize it. Here we're actually wanting to maximize it because both of these terms are negative, right? If we want to minimize G, then we actually want to maximize information gain and pragmatic value. So with information gain, you can look at this as what do I believe, or what will I believe, given the observations I think I'll come across when engaging this set of actions, versus what do I believe is usually the case when I do that set of actions. So really when looking at the KL divergence here, the only thing that separates these and makes it a non-zero divergence by not equating the same two things or juxtaposing the same two things is the why. So we're looking at a kind of scenario where it's like I'm seeking out doing things that bring about observations that actually change my mind. And ultimately, because of the particular terms here, it's kind of like saying I want to do things that change my mind about the association between what I think is going on and my actions. And the more intuitive way of saying that is simply I'm going to do things that help me get a better understanding between how I think the world works based on what I do, right? So imagine someone who opens up a textbook to learn something, right? And then you could start learning about, oh, I could apply active inference, or I could think about active. There are all kinds of ways that one could attempt to use active inference, whether it be for, brain computer interfaces, or it be used for, agent-based modeling in the social sciences, looking at, social media interactivity, but, patterns in networks, looking at neuronal dynamics. So it's that both of these are sort of like directives or incentives that we have. And then sort of the classic bit with active inference that's repeatedly stated in a lot of the literature when comparing it to reinforcement learning is that it's these terms that are directly implicated whenever people consider this sort of explore exploit trade-off. So this is a point I've made personally. I did a workshop at UPenn at a uh, conference last summer, and it was interesting to a lot of people who weren't familiar with active inference yet, but did reinforcement learning. Because with reinforcement learning, it's obviously not always the case, but there are at least times where people resort to defining some kind of term for what is exploratory behavior, which is sometimes it's as simple as like a epsilon greedy, meaning you essentially saying like, oh, the agent should always seek the reward point, 9 times out of 10. And then point one, like, or 10% of the time, just do something random. And then that way you can avoid getting stuck in a local minima. Um, but here we notice like, oh, as long as you have the equation for G, then exploitation and exploration are both scored on their own individually. There's no hard coded 10% of the time you do something random, right? So if expected free energy computation holds, and we find that at a variety of levels of, life, whether it be neuronally or for an entire person, or potentially even an entire group of people, depending on what level of the nestedness of Markov blankets you're looking. I mean, this is a way of saying, oh, we don't need to hard code a particular value to say when you should do something random. In fact, this isn't even random, right? Because you're actually making direct references to particular sequences of observation you expect, or states you expect, or actions you take. So that's sort of this is kind of a major strength of active inference. And for myself, as someone who's done a lot of kind of reinforcement related work in the past, this was one piece of kind of why I headed in this direction, because it seems so arbitrary to do epsilon greedy type stuff. Um, so is there anything in the few minutes we have left? Any final thoughts? Any final questions someone wants to pick up on? Reminder to everyone that we have a textbook coda. This was a nice video that Daniel and Ollie did some time ago. They did a sequence of book streams where they did rather much more in-depth sort of overviews of each chapter. Oops, sorry about that. And it's kind of a nice way within less than 30 minutes to go even deeper than I did during the course of this particular session. So with a lot of highlights on particular things that are worth putting your attention towards, if you want to get the most out of each chapter. And then for the sake of this cohort, since we are out of time, so chapter 3 will be next. That'll instead be the high road rather than the low road to active inference. So here we started with, we started in chapter 2 with Bayesian mechanics, took that route, and then chapter 3 will be about starting with the high road, starting from the free energy principle, starting with notions of self-organization, surprise minimization, see much more detail on Markov blankets, the idea of self-evidencing, including that trick about the sensory attenuation I mentioned earlier, predictive processing. So we'll reach there, and then chapter after that, chapter 4, we'll start to bring it back together. Chapter 5, significantly more about message passing, looking at actual like microcortical circuits in terms of like neuronal message passing and cortical layers. So for anyone interested in neurobiology, that's a particularly fascinating one. I always have a good time with it personally. So, all right, everyone. Thanks so much. I think we'll end there.
Thanks, Andrew. Bye, everyone.